Okay, thank you, Mr. Chairman, for the kind introduction. This presentation will deal with machine learning, fatigue, and additive manufacturing. The structural integrity of part produced through additive manufacturing process is a research topic of relevant interest, but since IM process allow to produce components with limited weight and optimal material distribution and exploitation, allowing for an effective lightweight design, as we can see here. But concerns are still present on the mechanical response of these parts, especially if fatigue loss are applied, since the fatigue response is significantly worse than that of part produced through traditional processes. And the reason is the different microstructure and mainly the presence of large manufacturing defects, as you can see here. Manufacturing defects induce a large experimental variability, and these complicate the prediction of the fatigue response and the subsequent design against fatigue failure. Here you can see some data on SNA plot obtained from the literature. But what is the reason for this large variability and scatter? The reason is that the specimens are produced with different process parameters, and subsequent post-treatment affect the microstructure and the defect population of the AM part, and accordingly the fatigue response. Therefore, a good idea is to take into account the process parameter as an input for the prediction of the fatigue response. However, the number of process parameters and post-treatment is high, above 10, and the experimental plan to find a correlation is not feasible. For example, with design of the experiment, the classic, we should obtain a very large number of data, and this is not feasible and too much expensive. On the other hand, a large number of experimental results are spread in the literature and are available, but they contain many information which cannot be exploited with traditional methodologies, so they are in a way useless, but they can be analyzed with machine learning algorithms. Therefore, the objective of this presentation is to prove the feasibility of predicting the fatigue response of AM parts starting from the process parameter by using machine learning algorithms, and validate the proposed algorithm on literature dataset to demonstrate its effectiveness. In particular, I will not focus will not provide you with detail about the code, the implementation. My idea is to show that this is feasible and can be a good solution for this kind of problem. Here you can see the process parameter, the main that we consider in our investigation, the building orientation, the input power and scan speed, the edge distance, the layer thickness, the heating temperature, the heating platform temperature, the powder size, and the beam diameter. We consider also some post-treatment like heat treatments and the corresponding heating treatment, whereas the surface finishing process like machining, polishing, and the other one are considered as Boolean feature. So they are set, it means that these are set to true if present and to false if not present. The process parameters have been all considered in all the machine learning algorithms which I will present. The post-treatment inputs have been varied depending on the material considered for the validation and if they are available in a good number for the material considered. Let's start describing the algorithms. The first one is a classic feed-forward neural networks, the so-called black box approach, I will call in this way in the next slide, maybe. And it is good to recall how they work. Neural networks are operators that replicates the brain structure, and they are composed by a layer structure. You can see in this image, in each layer is composed of different neurons, and they are fully connected between them. The weights and the bias in this equation are tuned in order to replicate the relation between the input and the output. This is a very straightforward approach. They find the relation between the input and the output, but it has some drawback. It is purely data-driven, so it requires very large data sets, and the prediction could be physically inconsistent. So you can obtain something which is not physical, since mainly based on data. This is the structure of the machine learning, the feed-forward, the black box algorithm that we have developed. In input, we have the process parameters and the applied number of cycles, and in output, the fatigue life or the fatigue strength, and therefore you can obtain the SN curve. We have, due to the disadvantages of these methods, we have moved one step further, and we have moved to the so-called physics-informed neural network. The structure you can see is very similar to the one that we have shown before, but in these algorithms, physical knowledge, prior physical knowledge are embedded within the machine learning algorithm. And therefore, in order to guide the algorithm to find a physical solution, physically consistent solution, and so we put physical constraint. How do we implement it? In this slide, it is shown. The physical knowledge from the Murakami model is used to build the model, and the neural physics-informed neural network recalls the widely known Murakami formulation. Indeed, according to this formulation, the fatigue, and by rearranging it can be shown that the fatigue response, the fatigue life is dependent on the microstructure and so on the Vickers harness, and it is proportional to it, and is inversely proportional to the area of the defect, to the characteristic size of the defect. So it decreases as the defect size increases. And this is well condensated in the Murakami formulation that I think all know. Here it is how this model has been implemented. We have the input and the output. We have a first neural network which models the influence of the microstructure. The input are the process parameter and the heat treatments characteristic. The second neural network model the input, the influence of the defect. In this case, we don't consider heat treatments since they are known to not influence too much the defect size. And then we have a third neural network which condensate the first two, the result of the first two neural networks with the number of cycles to failure in order to obtain the fatigue, the SN plot. The results, the effectiveness of these models, these algorithms, been validated by considered literature dataset taken, obtained by testing aluminum, typical aluminum alloy. We can see here from this graph that embedding physical knowledge allow to obtain a better accuracy, with the mean square error reduced by 20%. And here you can see the prediction obtained by considering the physics-informed neural network, so very good prediction. Here you can see that the physics-informed neural network provide good prediction even in the region, the high cycle, very high cycle fatigue region, where there are no available data. Okay, on the other hand, the feed-forward neural network has not a good trend. Here you can see another nice validation, in particular for the stress amplitude of 80 megapascal and 100 megapascal. We have verified the influence of the H distance. It is well known in the literature that the H distance, which is this one, it is an important parameter during the manufacturing of the specimen, is influence the fatigue response, and in particular the fatigue life decrease as the H distance increases. For the feed-forward neural network, the black box, we have not a good agreement. Okay, these are the experimental data. In this case, we have not a good agreement. For the physics-informed neural network with physics embedded, we have a good agreement with the experimental data, and we have also the same trend, the decreasing trend as we expected. So we have showed that physics-informed neural network works very well, but we may have forgot something, and what is wrong? What should be added to this model? The models are deterministic, okay, and cannot capture the experimental scatter. And as you know, fatigue of M4 parts or fatigue in general show large variability. So the experimental variability and the experimental scatter should be taken into account. Therefore, we have developed a new physics-informed neural networks. And for each data set, instead of considering deterministic point, the R90, C90, SN curve has been estimated. The R90, C90 curve, PSN curve, is commonly used for the fatigue design. It is the one which is schematically shown. It represents the lower bound at a 90% confidence level of the PSN curve with a 90% degree reliability. These curves take into account two experimental scatter. The scatter associated to the fatigue phenomenon, we know that the fatigue is not deterministic, and the variability associated with the estimation process with the confidence level. In this case, if, for example, this curve moves downward if we have less available data. So we take into account that we are estimating the curves from data which are not, from data set which can have a small number of data. We have estimated the R90, C90 PSN curve with the simplified OM method, which is well known in the industrial practice. And this is how we implemented it. We exploited the properties of the Bayesian neural networks. The input are the same, the process parameter, and the number of cycle to failures, and the output is the R90, C90 fatigue strength. The estimation, this neural network provides in output not a deterministic value, but it varies every time you launch the model. So we obtain, the estimation has been carried out 10 times, and so we obtain this green band, a band of uncertainty. In this way, we will be able to separate the uncertainty associated with the fatigue with the uncertainty in the prediction with the neural network. Indeed, there R90, C90 curve models the variability intrinsic to the fatigue phenomenon and to the uncertainty in the estimation process, whereas the iterative prediction with the neural network models the uncertainty associated with the neural network prediction. The models has been validated by considering a dataset on 316L steel, and you can see that we will not obtain a curve, we obtain a band of curves, and the experimental R90, C90 curves is within the estimated curves. Moreover, it is interesting to note that the estimation band increases as the number of cycles to failure increases. And this means why? Because here we have less data, and so the estimation with the neural network are less accurate. And this is what we expect to obtain. So to conclude very briefly, in the present work, I have shown the applicability of machine learning algorithm for the prediction of the fatigue response with additive manufacturing process. The input of this machine learning algorithm are the process parameter, the output of the fatigue life or the stress amplitude in order to obtain the SN curves. The neural network, black box, and physics-informed neural network approach have been used, have been developed, and the physics-informed neural network are characterized by better accuracy, and this proves the importance of embedding physical knowledge in this machine learning algorithm. Otherwise, they can obtain not physical relationship. The neural network physics-informed is based on the well-known Murakami formulation, model the influence of the microstructure and the defects has been validated on aluminum, silicon, tin, magnesium alloy, and is in sound agreement with the data. But most important, and very important, is also to take into account the uncertainty, since we are talking about fatigue, and fatigue rely on statistical model to take into account the variability. And in this way, we were able to separate the variability, the experimental variability, the estimation uncertainty, and the uncertainty associated with the machine learning prediction. And we have validated this on 316L steel. If you are interested in publishing on this subject, I have a specialist shop in applied science, or you can send paper also to material design process communication, for which I'm serving as editor-in-chief. But we can talk, if you need this, we can talk during the conference. Thank you for your attention.